So let's get started. This is section 3.1 from chapter 3. So we are going to apply differentiation or derivatives on real life applications. We're going to do those things. First, let us consider some definitions. So the first one, definition of extrema. Suppose if you are given a function f, which is defined on an interval I, which contain a point C, then we say f of c is the minimum of the function value whenever you have this condition. That is, the function value at c should be less than or equals to any other, x value in that interval. Okay, for all x in that interval. So basically, we know function value is smaller than any other value, means function has minimum at this value at c. Okay, so function has minimum and the value x value c. In similar way, you could define function f having maximum at c whenever the function value is now bigger than or equals to any other function value at x, where x belongs to that interval I. So how do you write this? So we write function f has minimum at the point c. The minimum value is nothing but the function value, right, at c. In similar way, you could write function f has maximum, means the maximum value, which is nothing but again the function value at c. Okay, so what I'm trying to say is, if you are asked to find the maximum value of the function, means you have to find the function value at c, that is f of c. Okay, that is the minimum and maximum value. The minimum and maximum value of the function are sometimes called as extreme values or extrema. Okay, so the minimum and the maximum of the function of any interval are also called as absolute minimum or absolute maximum. So basically, you are checking whether a function has minimum or maximum throughout the given interval. Throughout the given interval, some books use global mean or global max instead of absolute mean or absolute max. Both of them are fine. Okay, so you could use any of these terms to find the extreme values of function for the given interval. Look at these two pictures. First, you are given a function. You see the function domain is now closed interval -1 to -1 to 2. So it is very much clear that function has the minimum value here. The minimum value is y value 1, but minimum occurs at the point x is 0. The function attains maximum here. The maximum value of the function is 5, but it occurs when x is 2, right? So this function has both maximum and minimum. How about the second one? Look at the second one. Remember now, the domain is now open interval. That means these two endpoints are not included in your domain. That's why you see here there are two holes. So function is not defined at these two ends. Okay? That means now you cannot say this as the maximum because this point is no more in your domain here as well, right? Therefore, function has no max, but function has the minimum here. This is the minimum value, right? Function is defined at this point. The minimum value is 1. So that makes sense, right? So function is continuous in first case on a closed interval. the second case, function is continuous on open interval. Look at the third picture. Third picture, function has been defined into two pieces now. Function gx is quadratic function. That is true whenever the x value is not equals to 0. In other words, other than x0, function is nothing but quadratic. If x is 0, then function has just the value 2. So that is here, right? So function has the value 2 when x is 0. Here, on the quadratic function is not defined at 0. Other than that, function is quadratic function. So now, you see here, there's a hole, so function does not have, minimum value, but function has the maximum value here, which is 5 and 2. Okay, so that makes sense. Now there's a theorem we call the extreme value theorem. What is extreme value theorem? Suppose you are given a function f which is continuous on a closed interval ab. Then function f has both minimum and maximum. If function is continuous on the closed interval, always you could find minimum and maximum value of the function. That is true. But remember, function should have defined on this closed interval. Okay, so now look at this example. Consider the quadratic function x squared. We all know, right? X squared is quadratic function. It will be like parabola opens up. This is the graph of x squared. We all know, right? Look at the first one. Function is defined on this open interval. You don't see equal sign here, right? So function is, not covered in the endpoint at the endpoint. So -1 is here somewhere, and 2 is somewhere here. Now your function is given on this open interval. So the question is, do you find any maximum? Function is going this way, going up, but remember at this point function is now not defined because you are considering open interval, so this point is not included. Both the ends, right? These 2 points are not included in your function, therefore you will not find any max. But you see the minimum here. That's the minimum point, but you don't have max. That's why you see here minimum value is 0 at 0, but function, doesn't have a max. Now this one, number 2 case, function is now, this is for number 1. Number 2, again, we are considering the same x squared curve. Now the given domain is closed interval, right? Function is now defined. So you will find one point here and there as well. But the highest value here you will see when x is 2, function is 4, right? Because of x squared. So function has minimum here, which is 0, but maximum is 4. Okay, that is here. Minimum value 0 at x0 and the maximum value 4 when x is 2. That makes sense. Again, the third one, you see the open interval, so you will not find any minimum value because now your domain is restricted to 0 to 2. 0 and 2 are not included in your domain. So for number 3, the graph is like again x squared graph, but we consider only 0 to 2. Again, open interval. So you see here fall and here fall. So there's no minimum, no maximum. And the last case, number 4, again the function x squared, but now you have the domain one side included, right? You see, equal sign is here with 2, not with 0. Therefore, if you draw that graph, is again x squared graph, 0. Upper interval, but this side is now closed, right? That means now this point is good point included in your domain. This is not included. So here all here dot. So it is very clear that function has the maximum value here but no minimum. Therefore, function has no minimum and maximum is 4. Okay. So that is there. So you could look at the picture and find the maximum or minimum, or in another word, extreme points all the time you could find. That is extreme value theorem. Now another definition, relative extrema. If you could find an open interval containing a point C where function is maximum at that point, then we called f of C as a relative maximum. Okay, so here the important point is if you are talking about relative max or relative min, you are telling that you could find a point on an open interval. Point C is somewhere in open interval. There you will get either maximum or minimum value, which is called the relative max or relative min. Okay. Some books use local max or local min instead of relative max or relative min. Okay. So there are two things now you have learned. One is global max or global min. Another one is local max or local min. Okay. So for local maximum or local min, some books use relative max or relative min. Relative min. Okay. For absolute max or absolute min, some books use global max or global min. So keep in mind one more time, I'm telling you, if it is local max or local min, you are talking about an open interval inside. There should be a point C. Here you could talk about the closed interval. The point C could be here, anywhere, okay? Even it is possible to have here if it is closed interval. So basically absolute max min means you are finding the function value minimum or maximum throughout the interval, whereas local minimum, local maximum you are finding only within the open interval. These are the two, differences. Look at this picture. You are given a curve. So this is now, local max. This is local min, because it is always possible for you to find one open interval where inside you see the point. Here also there's possibility to find an open interval that is somewhere here. Inside the point you will get the minimum. So this is now local minimum point. This is now local max point, or relative max and relative min. Okay. So it is very easy to memorize. For relative max or relative min, you should have, say a turning point on the curve. So for the maximum, curve will be like this, opens down. For the minimum point, curve should be opens up. All the time, this is true for the local min and local min. There should be a turning point. You see here, there are two turning points, right? Now look at this definition. This is about the critical number. Suppose if you are given a function f, which is defined at one point C, if you see either, the function derivative at that point is 0, or if the function is not differentiable at C, then we call this point C as critical number or critical value of the function f. Okay, so critical number or critical value of any function f means you are finding the point or points, maybe more than one, where either the derivative of the function at that point 0 or function derivative at that point is not differentiable, mean not defined. Derivative is not defined. So that's the meaning, okay, for the critical points. Remember, when you study about the derivative of function, when you have a curve which has the sharp edges, the function is not differentiable at that point, okay? So if the function is differentiable, the function should move smoothly. The turn point is supposed to be very smooth, not like this pointer. If the function is having slightly sharp edge, then we call the function is not differentiable at that point. Okay, not differentiable. So in another word, this point can be considered as a critical point or critical value. You see here, this is a horizontal line, so always tangent 0. So this function has tangent 0 at C. Therefore, function has the critical value at that point. So there are two cases, right? Not differentiable or a slope 0 point. Both of them are called as critical values of the function. Okay. So now there's one more theorem. Relative extrema occur only at critical point. So relative maximum or relative minimum, remember the turning point I am talking about? We will see the turning point only at the critical point. That's the meaning. That is true, right? Look at this picture. Function has the turning point there, but we know this is the critical point. Look at this picture. Function has the turning point where slope is 0. Again, this is the critical point. So that's called this theorem. Okay. Relative extreme occur only at critical point. Okay. If f has a relative minimum or relative maximum at the point, then C is a critical number. That is true. If you find any relative max or relative min, that means that point is nothing but the critical point or critical value. Okay. Now, by considering these all things in your mind, we will summarize. How do you find extreme points on the closed interval? You are asked to find either maximum or minimum value of the function on the closed interval, like this. So these are the steps you have to follow all the time. First of all, find the critical value of the function. You know the meaning of critical value. Look for the points where function has slope 0. Find point C where such that function has the slope at that point 0 or function derivative at that point is undefined. Look for these 2 points, undefined. If you could find such points, those points are now going to be critical values. Once you know the critical value, find the function value at that point. Okay, then find the function value at the endpoint. Now compare all the values you have. Find the smallest value among those to find the minimum and to find the big one as a maximum. Look at this example. You are given a function, the interval now closed interval -1 to 2. Find the extrema of this function. Extrema means they are asking you to find max or minimum value. Okay, what is the first step? Look at this guy. First, you need to find the critical value, right? To find the critical value, first of all, you have to find the derivative of the function. So the derivative of the function, nothing but 3 times the derivative of x to the power 4 is 4x cubed using exponential rule we learned. Then subtract 4 times. The derivative of x cubed is 3x squared, right? Now this is my function derivative. Now if you want to find the critical value, you need to set this guy derivative function to 0 and find x. If you do that, you will get here 3 times 4 is 12x cubed. This is 12x squared, right? So that is my derivative function. So I'm plugging derivative function here. 12x cubed minus 12x squared. I'm setting this function to 0 and I'm solving for x. We all know how to solve this equation for x. So you could factor 12x squared and you will see here x minus 1, right? And you know now this will give you x squared 0 or x minus 1 0. This will tell you x is 0 or this will tell you x is 1, right? And solving for x. So there are two critical points you got, 0 and 1. Is it clear? The function f prime first derivative is very good function, right? Polynomial function. All the time polynomial functions are well defined throughout the real life. That means this function is good function. There is no bad points or undefined points are not there. So that means the derivative function is well defined. That's what this means. Okay. So now, after finding the critical values, find the function values at those points. So the critical value first is 0. So I'm finding the function value at 0. So remember the function, original function. The given function was here 3x to the power 4 minus 4x cubed, right? Now plugging 0 here into the function, you will find f of 0. That is nothing but 3 times 0 minus 4 times 0, which is 0. That is the function value at 0. Now find the function value at second critical point, 1. Again use the function plugging 1 here for x. So you will get this guy, right? 4 times. So if you simplify, this is 3 minus 4. That is negative 1. So basically I found the true value of the function on those critical values. Now look at the given interval. The given interval was negative 1, 2. So you have to check the function values at the endpoints as well. So now I am finding the function at the left hand point, negative 1. Function is here, plugging negative 1 now. Okay. So this will tell you 3. Negative 1 cube is negative 1. Here negative will be positive. So which is 7, right? Now find the function value at right hand point, which is 2. F of 2 is 3 to the power 4 minus 4 to the power 3. So 2 to the power 4 is 16. 16 times 3 is 48. Subtract 2 to the power 3 is 8. 8 times 4 is 32, which is 16. So list all the functions value like this. So I have so far 1, 2, 3, 4 values. 2 values are coming from critical values and 2 values are coming from the endpoints of the interval. So altogether I have 4 values. Now, you know, 1, 2, 3, 4. So left hand point 7, critical number 0, another critical number negative 1, and the right point 16. Among those the values, now you will find out the smallest and the highest value. Those are going to be minimum and maximum. Okay, or extreme values. So you got negative 1 and 16. So that's the way to do this problem. Okay. So now look at this picture. Now it's very clear, right? So this is the picture actually for this problem. If you graph the function, You will get this, and you will find all the things. Okay, maximum, minimum, and all. Now this is a good question. You could, you know, work on this problem like I explained here. Why don't you try that and try to understand? Okay, the same procedure. Now this is again finding the absolute extremum. Remember, absolute means the global value, right? You are finding the function value on this closed interval now. Again, like earlier we did, you have to find the critical values first by differentiating the given formula or function. So the given function was now trigonometric functions. Find the derivative of this function now. So the derivative of sine x is cosine x. So the derivative of sine 2x is 2 times cosine 2x. Now just use some trigonometric identities you learned, and you simplify these guys. Remember, cosine 2x could be written as by using double angle formula, cosine square x minus sine square x. Then do some algebra things and combine them, and we will get like this after factoring. Then you set it to 0 and solve for possible x values on this interval 0 to 3 pi over 2. So I believe you learned, guys, you learned about solving trigonometric functions in trigonometric course. Learned this already, right? So when you solve this equation for x, you will find out the possible x values. 0, pi over 3, pi, and 3 pi over 2. These 2 points are coming from critical value. These 2 points are coming from endpoints of the interval. Altogether, you find 4 points now. Okay, again, find all the function value at these 4 points. Function value at x0 is 0. Function value at pi over 3 is this value. Simply plugging pi over 3 into this original function, and you will find out that. And after that, it is obvious that this is the highest value and this is the lowest value. So you will get absolute max and absolute min. Okay. Again, this is a similar problem to this. Find the derivative, set it to 0, solve for x by using trigonometric identity functions and the things you learned. Then list the values. Now you see there are 4 critical values because the given interval was big interval, right? 0 to 2 pi. So you will find now 4 possible critical values for this function on this interval 0 to 2 pi. These are the possible critical values. Okay, pi over 2, 7 pi over 6, 3 pi over 2, and 11 pi over 6. These are the 2 endpoints you see. So you will find the function values and now compare the smallest and the highest among these values. Now you see this function has same minimum values at 2 different x values, right? Look at the picture. Yes, function has minimum value here and there. So function has 2 minima, 7 pi over 6. Yes. And 11 pi over 6. The function has same value. X values are different. And also function has the maximum value at x is pi over 2. So plugging pi over 2, you will get the maximum value, which is 3. Okay. So now you could try some problem from the textbook. Again, I will post all the completed notes later this week. So you need to practice problems from section 3.1. These are the problems you have to try from the text, from the book, okay? From the design. Try problem number 9 from 3.1 section. Then problem number 19. Then problem number 22. Anything else? One more. Problem number 29. Okay, so please try this problem. So question will be like finding extreme values or absolute values. So you follow those steps just now we learned. First find the critical values by equating the first derivative to 0 and solve for x. Then make the chart, find all possible function values at the endpoints and also at critical values. Then choose the smallest one among those values as minimum and the big value as maximum. That's the way. Okay. That's about 3.1. Now let's move on to 3.2. Rolle's theorem and the mean value theorem. What is Rolle's theorem says? Suppose you are given a function f which is continuous function on the closed interval ab, and if the function has good derivatives or differentiable on the open interval ab, and if the function has same values at a and b, then we will find at least one point inside the interval such that the derivative of that function at the given point c is 0. What does mean by that? Look at these two scenarios. First picture, function is continuous, differentiable because function has smooth, turning point and a smooth function, so it's all the time continuous and differentiable. I see the same function value here and there, right? You see this function value all the time d at these 2 points. So function f of a and f of b, have the same values, which is d. Once you have same y value, the function should turn somewhere inside, right? Because of function continuous. So function should have somewhere turned. That point is now going to be relative maximum. We all know that in relative maximum, function is having our first derivative is 0. Okay, that is here. But look at the second case. Function has the same value, but now function is not differentiable at this point, right? So function is continuous, but not differentiable on AB. So there are two cases here. So look at this note. From the Rolle's theorem, you can see that if a function is continuous and differentiable on AB, and if fa is equal fb, then there must be at least one x value where function has the turning point, that is this. When the differentiability requirement is dropped from the Rolle's theorem, still f will have the critical value, right? But may not be equals to 0 derivative. That's the case. If the function is differentiable, then only you will find the 0 derivative. If function is not differentiable, no need to be having 0 derivatives. Maybe critical point, maybe not differentiable, right? That's the case here we are talking about. Okay. but we consider as differentiable function, therefore we consider as case A, not like B. Then function should be having smooth turning point inside the interval. Okay. That is about the Rolle's theorem. Find the two x-intercepts of the function and show that function has the zero derivative at some point between those two intercepts. So first of all, find the derivative of the function, set it to 0, and find the horizontal, slope points. We all know how to find a horizontal slope form. Simply find the first derivative, equate to 0, and solve for x. So these are the 2 points function has 0 slope, right? Now find the function value, f of 1 and f of 2. Okay, so here you are just simply finding the x-intercept, not the derivative. Okay, simply find the x-intercept by equating the function to 0, and you will get 2 x-intercept. So f of 1 and f of 2 are same value, which is 0. So according to the Rolle's theorem, I could say, how can I apply the Rolle's theorem for this problem? My function fx is now x cubed minus 2x. Sorry, that's not x cubed. It is x squared, right? The given function is x squared minus 3x plus 2. Now I found two intercepts, x is 1 and x is 2. Now you could think of this as A, this as point B. So what is f of A? That is nothing but f of 1, which is plugging 1 into your function, you will get 1 minus 3, get 0. Now what is f of B? That is my second point, which is 2. That is plugging 2 into the function will give you 2 squared minus 3 times 2 plus 2. Again, this is also 0. So function has same value, right? So where f of A is equal to f of B. So I could use the Rolle's theorem. You see, Rolle's theorem also says if f of A is equal to f of B, then you will definitely find one point inside the interval, which is the, that is my A is 1 and B is 2. What does mean by this? This means you will find exactly, exactly a point inside this interval such that that point will give you 0 slope. So you look at here, you are finding the derivative and setting into 0 and finding the point where slope 0, that is 3 over 2. Yes, correct. 3 over 2 is within this interval, right? 3 over 2 is 1/2. 1/2 is within this interval. Yes, correct. So Rolle's theorem is satisfied here. Okay, so this is a way to show that function has 0 slope at some points inside the x-intercept. The next problem, we are given a function and find all the values c in the interval -2 to 2 such that f prime c is 0. Simply find the derivative of the function, set it to 0 and solve for x. Those are the x values we could consider as c. Okay, so that work is here. So the derivative of function is this, setting into 0 and solving for x. So these are the slope 0 points. Okay, get the picture now. If you try to graph this function, 4x cubed minus 4x, graph is exactly like this. So this picture is for x to the power 4 minus 2x squared. It's for different picture, right? Yeah, that's the picture for this graph. X to the power 4 minus 2x squared here. That is here. So you will find the two critical points. That is, in other words, zero's low points, -2 and 2. So you will find those two here. Okay. So this is about Rolle's theorem. Next theorem, mean value theorem. Suppose if f is continuous function on the closed interval ab and the function is differentiable on open interval ab, then you will find one point inside the interval ab such that the derivative of the function at that point is equals to this expression. Okay, what is this guy? Function value at the right hand point of the interval ab, subtract the function left point value at the interval AB, then divide by the difference between B and A, in other words, length of the interval, right? So this is the mean value. So mean means nothing but the average. Basically, you are finding the the rate of change of the function. Let's see. Okay, that is here. The physical meaning, there is at least one point you will find inside the open interval such that the instantaneous rate means the derivative is equals to the average rate. So this is the average rate, this is the instantaneous rate. Okay, all the time equal. Find all the points say in the interval 0, 1, satisfying the conclusion of the mean value theorem. You are given a function, you are given an interval. So the question is, could you find all the points C, right, which satisfy this mean value theorem? First of all, this is the mean value theorem result. You have apply this equation and find C. So given function is polynomial function, parabola, all the time continuous and differentiable. Okay, so now the given interval was 0, 1. So this is our A according to mean value theorem. This is B. Okay, so now function fx given, that is here x squared plus 2x minus 1. I am finding the derivative of that function, which is 2x plus 2, right? Simply find the derivative of x squared is 2x. The derivative of 2x is 2. Now, I am applying what? I am applying mean value theorem. So if you want to apply mean value theorem, you should know function value at a. That is, a is now 0, right? Function value is 0. Which is simply plugging 0 into the function, we will get 0 squared plus 2 times 0 minus 1, which is -1. Now find f of b. B is my second point on the interval, which is 1. That is 1 squared plus 2, 1 minus 1. Now this will be 2, right? I found f of a, I found f of b. Now let us apply mean value theorem. Mean value theorem says the derivative function evaluated at c is supposed to be equals to function at b subtract function of a, then divide by b minus a, right? Now your task is to find such c's. We don't know c's, we need to find out. You know the derivative function, right? This is the derivative function. Could you plug in there c? If you plug in c here, you will get f of c is nothing but plugging c here. Will be 2c plus 2, right? That means I'm replacing this guy by 2c plus 2. What is f of b? F of b is I got 2. F of a is -1. Then divide by b. B is 1 and a is 0. Now you have to simplify this equation and solve for c. You are finding c. So this will give you 2c plus 2 is equal minus into minus plus 1, which is 3. So c is 3 minus 2 over 2. That's 1/2. So the possible c value is just one value, which is 1/2. Okay. There. You could think about this one in the same way. Practice some problems from your textbook again from 3.2. So what are the problems you need to try from 3.2? From the textbook again, section 3.2. Problem number 13. Then problem number 22. And problem number 43. Problem number 50. That's it. So practice these problems from 3.2. Okay. So anyway, I'm going to post the solutions later this week. But anyway, first I need to try. I need to make sure that you guys try and you try to understand these all the things. And let me know if you have any questions. Okay.